Hello and welcome back to the third part of this lesson, and congratulations for making it this far. So without further ado, let's get right into it. So we are in the third part of our lesson, which is the dimensional consistency. Okay, so dimensional consistency. So basic principle is that equations must be dimensionally consistent. So each term in an equation must have the same net dimensions and units as every other term to which it is added or subtracted or equated. So for example, it's really easier to show this by example. So for example, the van der Waals equation, which has the formula, the P is equal to RT over V minus B minus A over V squared. So where P is our pressure and then V is our molar volume. So really, it is V bar because it's denoted as V bar there. So it's also V bar here, which denotes molar volume, just the units of liters per mole or any unit of volume per mole. And R is our ideal gas constant, and then T is our temperature, and then A and B, which is here and here, are our van der Waals constants. So, and additional information for you, we'll use our varies. So the values of A and B constants are found in our table 2, the 354, varies 8n. So the question here is what must be the units of A and the units of B for us to have a unit of, for example, ATM in our pressure. So let's see. So R, I have given you the units here. So R is equal to L. The units of R is L ATM uh, over mole K, mole Kelvin, and then the units of our temperature is Kelvin, so, and over our molar volume, which is liters per mole. Okay, and we don't know the unit of B yet, and then we are told to also find uh, the unit of A here, right? And we have V squared here, so means L per mole squared. So we are tasked to find the unit of A and B. So upon inspection, so the goal here is that our remaining unit must be in ATM. So from this uh, from the right hand side of our equation, uh, we see that B is being subtracted from the V. So that means they must have the same units, all right, for them to be subtracted. So okay, so we know now that B has the same units as V bar. Okay, and now um, A, we're now tasked to find A. So as you can see, there is a molar volume here, right? So for us to cancel and for us to have ATM left in here, so we must the units of A must have, or this must be the units of A also. So mole squared times the ATM, right? If you cancel the units, so uh, these will be cancelled. This liters per mole will be cancelled. These will be cancelled also, and this case will be cancelled, giving us the units of ATM and ATM minus ATM. Okay, so that's what it means. That's what it meant by uh, having dimensional consistency. Okay, so now let's move on to the next. And we have a sample problem here. So your handbook shows that the microchip etching roughly follows the relation d is equal to 16.2 minus 16.2 times e raised to negative 0.021 t. Then where d is the depth of the etch in microns or micrometers, and t is the time of the etch in seconds. What are the units associated with the numbers 16.2 and 0.021? To convert this relation so that d becomes expressed in inches and t can be used in minutes. Okay, so we will do here. Let's solve this. So um, D, we are told that D is in microns, okay? So D is in microns. So let's just factor this 16.2 out. So 16.2, so 1 and 0.21 T. So to convert these numbers to inches and minutes. So you must multiply them by their conversion factors, right? So 16.2, uh, that's in micrometers. Micrometers. So you want it to be converted to inches. So 1 micrometer is equal to 10 to the 6 meters. And 1 meter, or 1 inch, I should say, 1 inch is equal to 0.0254 meters. And then, uh, this is the whole equation, right? So, and then, RT, you must also convert that with, instead of in seconds, you will convert it into minutes. So we will multiply it by 60. So as you can see, 21. So it is the t is required here in seconds, right? So it follows that it has a unit of per second here. So if we convert that to minute, we must multiply it by 60. 60 seconds is in 1 minute. Okay, for the s's to be cancelled, and then the per minute remains. Also, it's the same here. The micrometer cancels, and then the meters also cancel, and leaving us with the units of inches and minute. So the final answer now is 6.30. Oh, so 6.38 times 10 to the negative 4. Then 1 e raised to 1.26. Right, and it conforms to the new units now. That's it. Let's move on to the next. Now, I will teach you about dimensionless numbers. So Reynolds number, yeah, it helps predict the pattern of flow and encountered in fluid dynamics, and it is really an important number for you to be familiar with, and it has a should I say, it has really a simple formula, and you can remember it because it is the formula is the D, the Reynolds number is equal to D, which is the pipe diameter times the diameter times the fluid velocity, and then times the fluid density over the fluid viscosity. So the way to memorize that is magtanim ay dV rho. Okay? So magtanim ay dV rho over E. So that's how you can memorize it. So it's really easy to memorize. Magtanim ay dV rho over E. So you can see here, these are the units. For example, we can give it as cm, centimeters, then for fluid velocity, centimeters per second, then the fluid density, grams per cubic meter, and then for our viscosity, we have the unit centipoise, or our abbreviated as C, then capital P, centipoise, which has the units of grams per uh, cm or centimeters second. So, for example, here these units are the example of the CGS units, or the centimeter, centimeter, gram, and second, or the CGS units. So what is the importance, or what are the importance of the Reynolds number? So it actually tells us the pattern of flow, and here are the pattern of flow. If the I say, if the units if the value of the Reynolds number is less than 2100, so it is considered as laminar. And then if it is between 2100 and 4000, it is considered as transition flow. And if it is greater than 4000, it is considered as turbulent. So as if you can see that the laminar, or for the visualization purposes, laminar flow is just like this. You can imagine, if you can imagine a water flowing like this, it's like sheets moving past each other without mixing, right? So it's really filed like that. And if you say it's turbulent, so it has eddies. It is a violent flow. All right. And transition flow, it's somewhere in the middle of this. So maybe a calmer, and then I don't know. I really don't know. Maybe I can visualize it like that. So why is it called a dimensionless numbers? So for example, I will plug all of these numbers here. So for example, it has the pipe diameter has the units of centimeters, all right? And then our fluid velocity is centimeters per second, and then our density is grams per cubic meter, and then our mu, our viscosity, is in centipoise, or in grams per cms. If you can see, we can cancel the units, right? So G cancels with this G, S cancels with this S, cm here cancels with the cm here, and the cm here. Now we are left with no units, so that's what we call that's why it is called dimensionless numbers. All right, let's move on. So I have here, so go check out table 3.9. So check out the table 3.9 in your Paris 8th edition for more dimensionless numbers. So If you can find there, the very first number that you can find there is the Biot number. So it's not funny, right? So go check out. Go check out. You can find there. You can find a lot more um, dimensionless numbers there. So let's solve a problem regarding the um, Reynolds number. So Reynolds number is equal to magtanim ID B rho over mu. dB, that's rho. That's rho. dB rho over mu. So let's see. So 3 inch. So and our velocity is given in feet, and also in our density is given in feet, and our mu is given in centipoise. So we have to convert these somehow for dimensional consistency. So 3 inches here, you can convert that to feet by dividing it by 12. All right. So for it to become feet, so 3, 12, so it's in feet now. And then our velocity is 6 feet per second, so it remains as is. And then also our velocity, our density, so lbm over cubic feet. And then our point, our viscosity is equal to cp. But we as you can see, these units are not consistent with our viscosity unit, so we have to multiply this somehow with a conversion factor that transforms it into an English unit also. So if you can find it in your Paris, the value 6.72 times 10 to the negative 4, and it transforms these this centipoise unit to an English unit. Okay, so if you multiply that, you get the answer to that. It is equal to 11,904.8. So judging from this value, we can say that the pattern of our flow is turbulent. Okay, turbulent. Next, sample problem. So the following equation is proposed to calculate the pressure drop across a length of pipe due to flow through the pipe. So determine the dimensional consistency of this equation. So we have the pressure drop is equal to 1/2 of the V, which is velocity, average velocity of the fluid, and then our L, the length of the pipe, D is the diameter of the pipe, and F is the dimensional coefficient called the friction factor, which is a function of the Reynolds number. So I will teach you how to get this number next time, but it requires you to solve for the Reynolds number first. So good thing I have introduced to you first the concept of the Reynolds number. So let's get that next time, and you need your Paris also to get that that number. So without further ado, let's solve it. So right, so RP must have it's a pressure drop, right? So it must have, if you remember the derived units, so we have there the unit of pressure, Pascal. And if you get the basic units of this, or the units of this in the SI, you have newtons per square meter. So that is in the left side. So that is our goal. And if you break these further, we know that kilogram, that newton is equal to kilogram multiplied by the acceleration. Acceleration. Okay, so your mass times the acceleration is equal to force. So F equals ma. That's N, Newton. And then you copy these two, this value in the denominator, which is m squared. So if you simplify this further, you will divide the m's here. So you will now have the kilogram. The remaining units will be kilogram per meter second squared. All right. So that's in the left hand side. Left hand side. So that's in the left hand side. What about in the right hand side? So the 1/2 and f there are dimensionless, so we can factor them out of our analysis. So b squared is we have the units of ms. So that's our standard unit for velocity, and then for our ld, so it's a ratio. For example, if your length has the unit of meter, and also the unit of your diameter has also the unit of meter, so they will cancel out. So and if you can see, they are not equal, right? They really are not equal, because as you can see, so it is not equal. So how can we solve that? How can we solve that? Actually, this is given in the book, right? So I'm not making this up. Hindi ko kayo niloloko, guys. Hindi ko kayo niloloko. So it is really in the book. So if you can see, yeah, in your other books, in the later books in your chemical engineering, for example, in your transport processes book by John Oakley's, it has the density term included in the it has the density term included in this equation. So what is lacking here is the density. Okay, as you can see, there is not a unit of mass here. So if we add the unit of density here, which is kilograms per cubic meter. So let's see if we can match the units in the right and match units in the left. Match units in the left and match it in the units in the right. So the units in the left, it remains as is. So now we have the meter squared second squared times our kilogram per cubic meter. So if you can, as you can see, this cancels, and then there is a 1m that remains here, and now our units are consistent already. They are the same. Okay, so that's how you can check for dimensional consistency. So last, I think this is not the last problem. So this is the second to the last problem. So if an orifice meter is used to measure the rate of flow of a fluid in pipes, so the flow rate is related to the pressure drop by the following equation. So U is equal to C, then square root of P delta P over rho. So where U is the fluid velocity, delta P is the pressure drop, and then the rho is the density of the fluid liquid, and C is the constant. And what are asked of us is what are the units of C and the SI system of units. So let's solve that. Okay, so as you can see, C is the we are required of the units in C of C here. So let's solve. In the fluid velocity, we can assign units here. So fluid velocity, maybe it has the units of meters per second. I already talked to you that the last time, right? So we have the units of C here. C, that's C. And then in the inside of our radical sign, we have our the units of our pressure. So the units of pressure is, maybe you can, for simplicity, we can choose pascals because it has the unit, newtons per square meter, right? Then over our density, which is kilograms per cubic meter. So we can break this down further. So ms c, as I showed you earlier, the unit of, um, the basic units of Newton is kilograms times the acceleration. All right, kilograms times acceleration over square meters. That's the meters there. Over the kilogram per cubic meter. And we have a problem now because we have this radical sign. So what we can do, maybe, we can square both sides. So we can square both sides for us to remove the, uh, c remains, that, we also can also square c. We also square c, and then the radical sign will be removed. Uh, Over kilograms per cubic meter. So now we can cancel, right? So cancel, and then the, meters here will also be cancelled here, and, what remains is this. This will be cancelled also. So and so we can see the final, uh, uh, final units, c squared. Uh, just don't mind this c, huh? Uh, because it's our, the goal. So if m multiply there, so m squared over s squared. All right, and then if we will get the unit of c here, I'll just, divide both sides uh, by this meters per second squared, meters per second quantity squared. So you can cancel this on both sides, and then we'll be left with 1, right? So meaning c is unitless. So, uh, c is unitless because there is not a unit was left in our calculation. So c is unitless. All right. Now let's move on to the last problem. So this is really actually easy. This is actually easy, guys. The thermal conductivity K of a liquid metal is predicted by the empirical equation. K is equal to A, times E raised to D over T, where K is the, uh, thermal conductivity with, actually, that has units, joules per second per meter per Kelvin, or watts per meter per Kelvin. Then T is a Kelvin, and A and B are constants. So what are the units of A and B? So, upon closer inspection, you can see that the K must have units of joules per second per meter per Kelvin. That also follows because this E has no dimension, right? So it is dimensionless. It's a dimensionless number. It follows that A must have the same units of K, right? So A must have the same units of K. So we got that one right. And then, B, it must be a ratio, right? So if you get a ratio, the units must cancel. So the unit of B must be in Kelvin also for it to be cancelled with the P, because the T has the units Kelvin, so it must be cancelled. So the units of A now, the unit of B now is in Kelvin, and the unit and we now have our answers. Okay, so it's not easy. So now I want you to try these practice problems. So these are easy problems. So the density of a certain liquid is given at the equation of the following form. So rho is equal to A plus Bp times E raised to Cp, which rho is density, T temperature, uh, P is the pressure, units of ATM, and then we are asked for the units of A, B, and C. And for the last problem, because I am only giving you two practice problems, is the velocity of the pipe in a pipe in turbulent flow is expressed by the following equation: U is equal to K, then square root or the tau over rho raised to 1/2. So where tau is the shear stress, newtons per square meters at the pipe wall, and then rho is the density of the fluid in kilograms per cubic meter, then U is the velocity in meters per second, and then K is the coefficient. So we are asked to modify the equation so that the shear stress can be introduced in the units of tau, which are pound force per square feet, and the density rho prime, for which the units are pound. This is pound mass, guys. If it doesn't have a subscript, it automatically translates to pound mass per cubic feet, so that the velocity U comes out in the units of feet per second. So show all calculations and give the final equation in terms of U prime, T prime, and rho prime, so our reader will know that the American engineering units are involved in the equation. So if you don't know what that means, so you can consult with me further for this problem, so that we can discuss it and you can solve it in your own. All right. So this really ends our lesson, our 3-part lesson, and congratulations for finishing this lesson. You're really happy. So please watch out for more lessons of chemical engineering here in my channel, and please do subscribe, like, and share these videos, and for to also help those in need of these kinds of video lectures. All right, bye, thank you.